Hello, everyone. It is nice to see all of you gathered today to our first CATIA Systems talk this year. My name is Gitana Strazdowski, and our topic today is Empowering MBSE with Simulation and Trade Studies on 3D Experience. My guests and speakers today are CATIA Industry Process Senior Consultant Jose Garcia and CATIA Industry Process Expert Kishore Tangadurai. During and after the presentation, you will be able to ask questions to our experts in the chat. They will answer them after the presentation. So we're ready to start. And Jose, Kishore, the stage is yours.
Thank you, Kitana. Hello, everyone, and welcome to this CATIA Systems talk discussing some challenges encountered during the system development lifecycle and how CATIA and Simulia can empower solutions. First, to talk a little bit about ourselves, I'm Jose Garcia, and I'm an industry process senior consultant, as Kitana said, specializing in MBSE and simulation. I'm a fairly recent hire to Dassault Systems, joined in April 2022. Before that, I worked in the IC and NASA. My educational background is electrical engineering with some MBSE programs. So, Kishore, do you want to tell the audience a little bit about yourself?
Sure. Thanks, Jose. So Kishore Thangadurai, again, I'm a teammate of Jose, industry process consultant as well, specializing in simulation, automation, and MBSE integration. I have about 15 plus years of experience in that, a little over 10 years with Dassault Systems, helping customers mainly automate and democratize their simulation workflows to enable simulation-driven verification and validation, and also perform MDAO on the 3D Experience platform. My educational background is I have a bachelor's degree in electronics and communications engineering from Anna University. Thank you.
All right, so what if we could assess design, reduce risk, and optimize performance of your system design by integrating realistic simulation at the early concept stage? Let's consider an aircraft system for which we would like to perform system analysis consisting of weight calculations from CAD models, some high-level CFD aerodynamics, and performance evaluation datasets in order to check satisfaction of design requirements. Today, we will be showing how the 3D experience will enable integration of domain expert simulations and enable trade studies across many system configurations to assist decision makers in identifying optimal solutions. To accomplish this, we will mainly leverage two of Dassault's solutions, CATIA Magic, also known as Cameo, and Simulia Process Composer. To give a brief overview of our agenda today, we'll first be diving into the importance of assessing design. And we'll go into the integrating of the simulations and enabling trade studies, and we'll finalize with a wrap-up and summary. The systems model already provides a descriptive definition of an architecture. However, the ability to assess its performance is incumbent on underlying specialized models developed by subject matter experts. Early design insights would be valuable to improve a design, but it is challenging to communicate and iterate due to expertise barriers, different data exchanges, and disjointed technical tools. These siloed processes are slow, inefficient, and non-scalable. They introduce additional risk of human error and lack rigorous traceability. They also lack the opportunity to perform meaningful trade studies because we can't run them thousands of times without large hits to personnel availability. A model-based approach is now the standard for modern system design, and its next step is integrated simulation. SMEs can develop and share their simulations with system engineers by utilizing the 3D experience. The system engineers can then integrate those templates directly into the system model, eliminating siloed processes and enabling traceability and scalability. The net benefit is an increase in analysis frequency and accuracy, thereby reducing risk earlier in the design cycle. So let's dive into how we can integrate these simulations. To go through these stages of the workflow, first we'll cover the creation of the shareable model templates to the right. So I'm going to hand this off to Kishore to cover.
Thanks, Jose. So first, a SME will develop and validate their models just as they do today. These can be product virtual twins on the 3D Experience platform, or simulations built with in-house tools and external applications. Second, the SME will compose a simulation process to define a workflow of their model and data processing activities. We will dive further into this in the simulation process in the very next slide. Third, the SME will configure the execution of the simulation process to create what's called a template. This template is then shared with the systems engineer for them to add to the system architecture model and be able to launch an integrated simulation. So to recap, we have SMEs controlling and validating their high fidelity models and specialized simulations in formats they use today. SMEs composing simulation process and templates from their models and sharing them. And systems engineer utilizing these shared templates to perform system analysis. These templates directly document the SME's workflow, and inefficient communication loops have thus been removed so that the systems engineer can now leverage the subject matter expertise for as many analysis iterations as needed without having to tie up the SME availability. So let's now talk about composing that simulation process. The Process Composer application provides you with a no-code drag and drop interface where you can define anything from a simple to a complex workflow. Within these workflows, you can define the necessary parameters, which kind of represent in the systems engineering the value properties, and logic to launch different tools, pass information between them, and define where they would execute. Once you have the workflow defined, you would then create a simulation template exposing only those critical parameters for non-experts to feed in. So to reiterate, the open data format and adapters enable us to connect everything from the 3DEXPERIENCE virtual twins, in-house tools, and external applications, including code scripts, and build a template that can be then leveraged and used by any non-expert and systems engineers. So in this example, like Jose said, we are looking at an aircraft architecture. And to help Jose as a systems engineer here, SME has developed 3 different simulation templates. It's the weights calculation at first that's made based on a parametric CAD model. It calculates the weights from the preliminary aircraft geometries, dimension updates. They also have an aerodynamics calculation. This is based on fluid simulation, estimates the lift and drag of the aircraft based on the geometry updates. This essentially is executed on an HPC cluster. We also have a reduced order model developed for this, for it to be executing in a much faster fashion. And then finally, a range evaluation. This is an Excel-based spreadsheet. It estimates the range based on the aircraft dimension updates, and also the weights and aerodynamic outputs calculated in the above two simulations. So to look at this example, let's pass it back to Jose.
Thank you, Kishore. So we start with a diagram within Cameo showing the aircraft, its subsystems, requirements, and analysis context blocks. We create a parametric diagram and we bring up a web browser window where we are already logged into the 3DX platform. From the web browser, we can drag and drop the SME created templates onto the diagram. Cameo automatically creates input and output pins, and the parametric equation wizard recommends parameter connections. We drag and drop the other 2 templates and set parameter connectors, which will enable us to pass values directly from the SysML model to the SME templates. In addition to parametric diagrams, we can also integrate templates into activity diagrams. Here we have dragged and dropped the templates from the 3DX platform and connected the pins in a similar fashion as the parametric diagram. We will run the simulation, and on the left you will see the system of interest and some predefined input parameters. When we start the simulation, you will see the parameters being read and fed into the templates. Once the templates have the required inputs, they will begin executing on the platform and returning results back to the Cameo model. For this example, we want to calculate the range for an aircraft given a set of inputs to see if the design can satisfy a requirement. At the end of the simulation, we will hover over that range parameter to see the associated requirement text, and you can already see that the range value is highlighted in green, telling us that we pass given the provided inputs. All right, let's dive into how we can enable trait studies from this. In the previous video, you saw me run a simulation that evaluated range requirement satisfaction of a single aircraft design. If we wanted to evaluate different system configurations, we might create an instance table and run simulations for those configurations. We find that this approach can be tedious. Simulations are ran sequentially on your local workstation and likely slow. System alternatives are your best guesses without true design exploration or optimization. So let me pass this off again to Kishore to discuss how we can address these gaps.
Thanks again, Jose. So yes, like Jose said, what you saw in the first video was a single iteration. And as you want to perform or explore the complete trade space, let's look at how the 3D Experience platform can help you here. The application of choice here again is Process Composer. As we saw in the first section, Process Composer uses adapters to connect with external tools and launch those tools. So we have the Cameo or MBSE adapter here that ties in your system model. The system model can be integrated at any level of the system configuration. Once you have that tied into this workflow or as part of the process, it can then be driven using the driver adapters that uses different techniques that are built into the platform, like DOE, optimization, and reliability techniques. To dive a little bit deeper on those, what the 3D Experience platform has is we have 11 different design of experiment techniques that help you efficiently assess the design space or the trade space. We have 16 optimization techniques to drive design towards desired objectives. That also includes DS proprietary hybrid optimizers. We also have Monte Carlo simulation for reliability to evaluate robustness of designs by introducing uncertainties and tolerances. Okay, so as you tie into one of these existing techniques, what we also help you with is automatic generation of that trade space or design space. You specify the upper bounds and lower bounds and the different parameters or criteria, and it automatically builds the design matrix for you. Not only that, thanks to the distributed execution capabilities of the 3D Experience platform, we are able to execute these in a fast and parallel fashion. And like we talked about before, you can execute this system model at any level. So we run that, different alternatives are generated. So in this case, we are changing the aircraft's dimensions to see which aircraft might meet our requirements best. So we have generated tons of different alternatives. What next? Now we have tons of data in our hands. How do we proceed from here? To enable you perform that trade-off and pick and process these data and understand what might be the best design, we introduce Results Analytics. Results Analytics is a web-based widget. I like to call it the decision support tool in the 3D Experience platform that helps you easily manage all these large data sets that were generated. It automatically filters, ranks, and scores all these different alternatives and enables you to perform trade-offs thanks to its rich visualization capabilities. Also, to highlight here, it helps you export an FMU, a reduced order model, from these huge data sets, and also provides you the capability to export and tie back to the requirements that you begin with. So let's take a look at an example in this case. So we are going to use the same aircraft system model to calculate the range. We're going to drive that using an optimization adapter to explore the complete trade space to see what design alternative might best meet our requirement. So I have the Cameo adapter here. That blue box is called an activity. And the Cameo adapter, of course, is going to launch the application. And you can see that we have parameters defined which corresponds to the value properties of the system model. So once I have that integrated, then I can drive that using an optimization adapter. There are various optimization techniques available. We are using the adaptive DOE technique. The section here shows the configurations of the optimization. In this case, we are using 10 different combinations, and I think 42 points per each iteration. And I'm able to also quickly define the design space or the trade space. These information can be directly read from your system model if it is defined so. Otherwise, you see that you can define quickly the lower bound, upper bound, step size, and whatnot to define the trade space or the design space. You are also able to define constraints and objectives, of course. In this case, we are trying to maximize the loaded weight and also the range. On top of that, like I mentioned, using the 3D Experience execution backbone, we are able to execute this in a parallel fashion. So once I have that workflow finalized, I'm going to run this. To highlight the distributed capability of the execution, lets you run this on server-side simulation, or if you're using desktop models, it could be distributed to run on multiple desktops in a parallel fashion to quickly generate the data set. So that execution has happened, and we have generated the data set. How do we visualize and post-process this data set to understand what this data set is telling us? To do that, I've loaded the data set into results analytics. This, like I said, is on a web browser. It's a widget on a web browser. As you can see at the bottom, it has different tabs that kind of guides you through the different steps required to achieve the goal here. So the preview tab just gives you an overview of the data set. It lets you explore, okay, how the inputs have been varied and accordingly how the output changes, and to understand the complete space. The define tab, you define your problem definition. It automatically inherits the values that we defined in the optimization adapter. So we set some lower bounds and upper bounds and objectives like for range to be maximized. All those are automatically populated here. You are also welcome to manipulate and change these. Not only that, we are not showing that in this demo. You could also tie this directly with requirements. As you can see, there is the requirements tab. You could also tie this directly with requirements and read these information from requirements if those are tied in. So based on your problem definition here, Results Analytics is going to automatically rank and score these different data set and provide you with visualization capabilities. There are tabular views and there are also plots and charts. First, let's take a look at the scatter plot of range versus loaded weight. As you can see, the data set is color-coded for you to quickly eliminate anything that is red is infeasible design that did not meet at least one of the requirement, and helps you quickly narrow down on points that might be of best interest for you. Returning to the tabular format, like I said, anything that's red as infeasible design did not meet at least one of our requirements, so I can eliminate those. And then you see there are two different color codes available here, green and white. Everything that's green is called a best alternative. So by default, the system recommends those because those alternatives meet particular objectives, and you cannot find a better alternative without compromising on a different objective in that particular case. Then there are the white alternatives, those are called dominated. That is because there is a better alternative in that green space, in that best alternatives, that meets those requirements in a much better fashion. So let's eliminate those dominated results set as well. And I have a good collection of best alternatives in this case. So what? You're not just limited to that. You can further dive deep into this. So let's, in this case, take, let's say, 5 different alternatives and compare those side by side to see of these provided best alternatives, which might meet our requirements best. So I select that, switch to the compare tab. Again, it highlights by comparing those alternatives against each other to see if there is a particular alternative that meets a particular objective better or worse. The given objectives being cruise velocity, weight of the payload, and range. We also have a spider plot or radar plot in this case. Of course, the further the point, the better it meets that particular objectives. So we have some design alternatives that does better in a particular objective alone, like either weight or cruise velocity or weight of the payload or range. But then you see that little green alternative 378 there that has a good balance. So that might be a good combination for us to work with. You're not just limited to these visualizations. You can also perform trade-off analyses from here. To do that, you switch to the Collaborate tab. In the Collaborate tab, again, you get the same visualization, tabular visualization to side-by-side compare those. But you see that based on everything given the top priority or highest weightage, the system is by default recommending that alternative 131 best meets your requirement. Okay, so what if we want to change the weightage on one of these? We, of course, want higher priority or more importance on weight of the payload and range, but maybe we could compromise a little bit on the cruise velocity and see then what happens. So if we reduce the weightage on cruise velocity, you see that in real time, the system is automatically re-ranking and scoring the data set to now recommend that alternative 378, which we already looked at in that spider chart, might be your best alternative given this changed set of weightage. So what? We did a lot of thought process went to this, a lot of decision making went into this, and now finally we are picking to say 378 is our best alternative. How does Hound capture all these things? So here you are able to select something as a recommended alternative, thus capturing all the thought process and decision making that went into this process. Not only that, you are also able to then export that from here to tie in and update a requirement if that exists, and this demo will show a requirement. You could also tie this back and update your system model to say, hey, given that different trade analyses, we found a particular design or multiple designs which might be of best interest for you, and tie it back and update the system model for, say, an instance table or whatnot. All right. So to wrap up and summarize what we saw so far, the systems engineer starts with a set of requirements and inputs from other stakeholders to develop the system architecture. Meanwhile, parallelly, design and analysis engineers are building their models. These higher fidelity models can then be tied into the system model via the drag and drop capability that Jose showed earlier to run and validate your system model. Once you have the executable system model, that can then be driven using the DOE or optimization adapter to evaluate the complete trade space. That data can then be loaded into results analytics to perform trade-offs and evaluate performance against specific targets. These learnings can then be fed back to evolve and improve the system.
All right, so today we covered how you can assess design, reduce risk, and optimize performance of your system design by integrating these types of realistic simulations. We showed how the 3D experience enables integration of domain expert simulations and enables trade studies across many system configurations by leveraging CATIA Magic and Samoya Process Composer to ultimately assist decision makers in identifying optimal solutions with Samoya Results Analytics. And here we have a couple takeaways and summaries from our presentation today, but that's the end of our briefing, and we can take some questions now. Thank you.
Thanks, everyone.
Thanks a lot, Jose and Kishore, for your presentation, for very technical presentation. So actually, we have a few questions that I got in front, so it's really good for us to know, for our audience to know. So how to start, and like where to find information on how to set up the solution.
Kishore, do you want to take that one?
Sure, yeah. So we have these presentations available in the MBSE conference, and we have these recordings here. To be able to get the documentation, I think it's CATIA Magic 22X version is when this is completely available as part of the documentation. So there are, actually, it might be the exact same aircraft example that was documented in there with similar screenshots to know how to get the integration going, what additional information is needed for the integration, and talk about the additional plugins that might be needed to integrate. Yeah.
Okay, and also just in a few words to say what are the biggest benefits for this solution and for whom?
Right. Yeah. So we think this could be applicable to many different people on your team, but we think it especially could help your system engineers or your simulation experts. There's obvious benefit in being able to, as we said throughout the presentation, remove some of the existing siloed processes and data sets that exist today. Instead of having to have this human-to-human handoff of information or requesting that people on different teams run a simulation for you, you can have them share those simulations directly on 3DEXPERIENCE and integrate them yourself, or vice versa, use a CATIA system model to run and use as input for your dataset simulations.
Okay, so thanks a lot for your time. Thanks a lot for the users, for the audience who connected and spent almost half an hour with us. And we are done for now. So for the replay, you may visit our community. And if you have questions, please write your questions in the community so the speakers would be able to answer. We will meet in a couple of weeks on February 22nd for our next CATIA Systems talk. And wish you all the best for this day and for the week. Have a nice day.
Thanks, everyone.
Thank you, everyone.